Okay, this is our final video, tutorial number 3 in lesson 7.1. And we're going to talk about manipulating equilibrium expressions when we add or reverse reactions. So, we are manipulating equilibrium constants. And the equilibrium constant of a reaction in the reverse is the reciprocal of the equilibrium constant of the forward reaction. What does that look like? If we have N2O4 going to 2NO2, this is our reactants, these are our products, this is our equilibrium constant expression. This is to the second power because this is a 2 over here. And it equals 0.212 at 100 degrees Celsius. Remember, our equilibrium constants are different at every temperature. If we look at the reverse reaction, if we make these are reactants now. We're going backwards. This becomes our products. So we're going this way. Then our equilibrium constant expression is written as the concentration of N2O4 on top, because that's our product now, over our reactant, NO2 to the second power. So this is now in the denominator. So we flipped this. We flipped this expression. Therefore, our equilibrium constant is the reciprocal of what it was initially. It is 1 over 0.212 because we have flipped our expression. What was in the denominator is in the numerator. What was in the numerator is now in the denominator. And 1 over 0.212 equals 4.72. So when a reaction is in the reverse, then the equilibrium constant is 1 over what it was going forward. Second way of manipulating a reaction is to multiply it by a number. Here we have an original reaction. In this over here we've multiplied it by 2. We've 2N2O4, and over here 2 times 2 gives you 4NO2. So we've multiplied this whole reaction by 2. This is what we get. When you multiply a reaction by the number, you take the equilibrium constant to that power. So this equilibrium constant here is equal to this one to the second power. So if I take this whole equilibrium constant here, I've rewritten it, and because I'm multiplying it by 2, I'm going to raise the whole equilibrium constant expression to the second power. And if I do that, this is what it equals. NO2 to the fourth, because 2 to the second power is to the fourth power, and down here N2O4 to the second power, because this was to the first. So you multiply them to get that to the second. So I took my Kc here and I raised it to the second power because I multiplied it by 2. So if you multiply a reaction, you raise the equilibrium constant to a power. And finally, if you have an equilibrium constant for a net reaction that's made up of 2 or more steps, then the Kc for the reaction is equal to the product of the 2 reactions you added. Let's see what that looks like. So these are the 3 things we've talked about. This was the first one. If you take the equilibrium constant of a reverse reaction, you take the equilibrium constant of that reaction is equal to the reciprocal of the first one. Then the equilibrium constant, if you multiply a reaction by a number, is equal to the first equilibrium constant to the power, that is that multiplication number. Now we're going to talk about this. So if you have 2 or more reactions that you add, and in this case we're adding A plus B going to C plus D, and the equilibrium constant is equal to K, and a second reaction, C plus F going to G plus A, and these are in equilibrium with the second equilibrium constant. If I add them, C's cancel, and what else cancels? The A's cancel, and this is my net reaction, B plus F going to D plus G. So I've added these reactions, canceled everything. I could have written it like this. A plus C plus D plus G plus C plus A, but I would have had to cancel them anyway. when you add two reactions, you multiply the equilibrium constants. So here, K3 is equal to K1 times K2. So write that down. So you guessed it, now we're going to use those three rules to figure out equilibrium constants for a reaction. In this case, this is our net reaction. And we know the equilibrium constants of these two reactions. Of reaction, we'll call it 1 and 2. Make this a little bigger. Okay, so I need to figure out what I need to do to these two reactions in order to make them add to this one. So I've rewritten the first one. And this is my net reaction, which I've now written on the bottom. So if I want to add these two to get to this, well, I have HF here, but here it's 2HF. So I'm going to have to multiply this by 2. So I'm going to do that in blue. So 2, 2, 2. Now, if I multiply this by 2, what do I have to do to this equilibrium constant? Let me look on my notes. Oh, when I multiply, I have to raise that to a power. So I'm going to take this, and I'm going to raise it to the second power. So it's going to equal, we'll figure that out in a second, but it's going to be raised to the second power because I've multiplied this by 2. Actually, let's rewrite it now. So 6.8 to the second power is 46.24, and 10 to the negative 4 to the second power is 10 to the negative 8th. Okay, now I have over here C2O4 to the minus 2. This is the oxalate ion, and in this reaction it is in the products. Here it's a reactant, so I need to flip this reaction. So I'm going to do that in a different color. So let's flip this reaction so that I have C2O4 minus 2. Oopsies. So I've flipped it now. I put my reactants as my products, and my product as my reactant. My reactant is my product, and my products is my reactant. But since I flipped it, what do I have to do to my equilibrium constant? Let's look at our notes and check that out. Oh, if I flip a reaction, if I take it in the reverse, I have to take the reciprocal. So I need to take, for this, 1 over Kc, since I'm flipping this, which is 1 over 3.8 times 10 to the minus 6, which is a very large number. It is, I get 263,158. I should really round that to 3 significant figures. Or 2, I'm not going to. Okay, so I flipped that. Now, third process, I'm adding these. I'm going to need more room. Oh, that's not going to work. I'm adding these two equations. So if I add them, let's see what happens. If I add 2HF plus C2O4, the H's are going to cancel out. This 2H cancels. So I have 2HF plus C2O4 on my reactants. My products, I have 2 fluoride ions plus H2CO4. So now the way these are written, they add up to this final reaction. When I add two reactions, what do I do to their equilibrium constants, which are here and here? Look on your notes. If you add two reactions, you multiply the equilibrium constants. So the final, let's do a different color. The K for this reaction is going to be equal to, we're going to call this one K1 prime, and this one is K2 prime because we adjusted them. It's going to be equal to K1 prime times K2 prime. So the equilibrium constant for this final reaction is 46.24 times 10 to the minus 8th times 263,158, which is going to equal, this equals 0.1222 2. So that is our K for this reaction. We used all 3 steps to manipulate to find the equilibrium constant of this final reaction. Okay, this is a similar problem. You can pause it, solve it yourself, and then fast forward, or you can work with me to solve the problem. We are looking for the equilibrium constant for this reaction, and we're given 2 reactions. They all occur at 25 degrees Celsius, and these are our equilibrium constants. This is for this one for this one. So first we need to see how we manipulate these 2 and add them together to get this reaction. This is the final reaction I want. So I have HNO2 up here as a reactant. Here it's a reactant. There's 2 of them here and just 1 here. So I'm going to take this reaction, write it here, but multiply it by 2. Didn't mean to keep the time running while I did that. So I multiplied this reaction by 2, this one up here, the first one by 2, and because I multiplied it by 2, I took the equilibrium constant for this reaction and took it to the second power. So that's what we have here. Now my other reactant here is SO3 minus, and this should be a minus 2 up here. It's a typo. So I'm going to have to reverse this reaction. So let's do that. So I have reversed this reaction and put it here. And since I reversed this one, I had to take the reciprocal of this equilibrium constant to get the equilibrium constant of the reversed reaction. So the equilibrium constant for this reaction is 1 over what it was for the going the other way. Now I'm going to add them up and see if I get this. So I have 2 HNO2s, that's down there. I have SO3 2 minus, that's there. I have no H plus here, but these are going to cancel. This is a reactant, this is a product. I cross them out. On my product side now I have 2 NO2 minus, 2 NO2 minus, and H2SO3. So these 2 add up to this net reaction if you cancel things that are on both sides. If I'm adding 2 reactions, what do I do to their equilibrium constants? I multiply them. So my equilibrium constant for my pink reaction here is going to be equal to the first one times the second one. So it's going to be equal to 4.5 times 10 to the minus fourth to the second power, so we'll put that whole thing in brackets. And then that multiplied by 1 over 1.1 times 10 to the minus 9. So let's simplify this before we plug it into our calculator. So I can rewrite this as 4.5. We have to square the 4.5 before we squared the second part. So 4.5 squared is 20.25. That's going to be multiplied by 10 to the minus 8th, because minus 4 times 2 is minus 8. And that's going to be multiplied by this 1 over 1.1 times 10 to the minus 9. So minus 8 divided by minus 9 is really minus 8 plus 9. So my K is going to be equal to something times 10 to the 1, because minus 8 plus 9 is 10. 20.25 divided by 1.1. You could also just put this in your calculator. 20.25. So 20.25 divided by 1.1 is 18.41 times 10 to the 1, so that is equal to 184. That's your answer. So one more practice problem. We want to find the K for this reaction, and we're given 2 reactions. We're given this one, and we're given this one. We need to find the reaction for this one. So let's see. We have NH3 here as a reactant. Here it is a product. So we're going to have to flip this reaction. So let's write this flipped. It's going to be 2NH3 in equilibrium with N2 plus 3H2. I think I wrote that wrong earlier somewhere. And since I flipped it here, I'm flipping it, I have to take the reciprocal of its K. Its Kp was 1.04 times 10 to the minus 4, but the Kp for this reaction, K prime, is going to be 1 over 1.04 times 10 to the minus 4. Now, my other reactant here is 3I2. I have I2 over here, but not 3, so I'm going to rewrite this, but multiply it by 3. 3H2 plus 3I2 in equilibrium with 3 times 2 here would be 6HI. The K for this reaction was 54, so the K for when it's multiplied by 2 is going to be 54.0. I multiplied it by 2, so I'm going to take it to the second power. Now let's see what happens when I add them. If I add them, 2NH3, that comes down here. The 3I2, that comes down here. That's good. I have H2 on this side and 3H2 on both sides, so I'm going to cancel them. Near. Now on my product side, I have N2, that's over there, and I have 6HI. Good, so it adds. So if I want the K for this reaction, I need to multiply my Kp1 and my Kp2, which is 1 over 1.04 times 10 to the minus 4 times 54.0 to the second power. And you can do the math there. Are you chatting with strange people?
No.
Oops, I recorded that. And so now you get a huge number, 28038461 for your K. And if we rounded this to 3 significant figures, it would be 28.0 times 10 to the 6th, but that's really incorrect. It should be 2.80 times 10 to the 7th. And that is your answer. And we are not yet done. So moving on. We're now going to talk about heterogeneous equilibrium. What does that mean? That means when you have equilibrium and you have things in different states. Gases, solids, aqueous solutions, a mixture of different states of substances. And what I want you to write down in your notes is that the concentrations of pure solids and pure liquids are constant, meaning they do not change. So write that down. There's a blank. The concentrations of solids and liquids are constant. Both can be obtained by dividing the density of the substance by its molar mass, but they don't change. If the temperature is the same, the concentration of a solid is the same, no matter how much of it you have. Therefore, we do not write the concentrations of solids, pure solids and liquids, pure solids and pure liquids, in our equilibrium constant expressions. We do not write the concentrations of pure solids and liquids in our equilibrium constant expressions. We only include concentrations of, you have a blank in your notes for this, aqueous solutions and gases, because the concentration of a gas can change depending upon its pressure, because there's so much space between those molecules. So this is what you fill in for the blank, for what you do include in concentrations in equilibrium expressions. So you can see here in this one, you have this concentration, the concentration of the lead ion. It's aqueous, it's a solution, so the concentration can vary. The chloride ion concentration can vary because it's aqueous. But there's no denominator, there's no reactant because this is a solid and the concentration wouldn't change. So you don't include that in there. It may seem weird, but you don't. And it's because as long as some of these solids remain, this is the reaction, this reaction going on, remain, their concentrations will stay the same. So they won't affect the equilibrium constant because they're not changing. Or they're not changing proportionally, I suppose more correct. Okay, for the last slide in this video, we're going to think conceptually. We have 4 situations And we're going to think about if each one is left alone, we're going to think separately, evaluate them individually. If they're left alone, if they will attain this equilibrium of calcium carbonate in equilibrium with calcium oxide and carbon dioxide gas, which was the picture I think we saw before. So first situation, letter A, we have CaCO3, a solid. So if we leave that alone, what's going to happen? Well, if calcium carbonate as a solid decomposes into calcium oxide and CO2, if you leave this alone, it will reach equilibrium because it will decompose into calcium oxide and CO2. So the answer here is yes. If you leave this alone, it will decompose. Okay, now we're going to consider the second situation, okay? Letter B. In letter B, let's make this a little bigger. We have, oopsies, CaO as a solid, and we have CO2 over here, one of our products, and the pressure is a pressure greater than Kp. So let's think about what Kp means for this reaction. For this reaction, Kp is CO2, the concentration or the pressure. That's pretty much it, because you don't write this one and you don't write these in the equilibrium constant expression. So if the pressure is greater than the pressure needed to reach equilibrium here, well, we haven't really learned this yet, but if the pressure is greater than this pressure, because that's only all that is equal to, this is going to, the concentration of this will adjust downward so that it equals this. If it adjusts downward, that means it's going to move this way. It's going to create, the equilibrium will move to the left. This is called Le Chatelier's principle. So the gas will create, oops, wait, let me make some sure. Yes. And because I wrote this wrong, so what will happen is these two things will combine, because this is our other product, and they will combine to make CaCO3. So it will reach this equilibrium because you have some of each of these things, and they can combine to move in this direction. So the answer here is yes. Okay, next question. I'm going to do this in another color. Cross this out. If we have CaCO3, solid, and CO2 as a gas, and the pressure is greater than the value of Kp, which is equal only, this would want to come down so that it would equal Kp. But we only have this substance and this substance. We don't have any of this. So equilibrium cannot be reached here because this cannot combine with calcium monoxide to create more calcium carbonate. This reactant doesn't exist. And because the pressure is greater than the equilibrium pressure for this gas, this is not going to decompose any further. The direction the equilibrium would go left. We're going to talk about that more when we talk about Le Chatelier's principle. So the answer for this one is no. And then finally, okay.